This class is on the last lecture on the module of NDT techniques which are used in machinery condition monitoring, and today I will be discussing about techniques of radiography, dye penetrant test, and finally visual inspection, which is also done and necessary for machinery condition monitoring to know the status of a machine component in terms of whether cracks and defects have occurred, whether voids are there, whether the weld has been perfectly done, etc. So, let us first look into what this radiography is. Radiography is otherwise also known as the X-ray technique. So, basically just to recap, we had in NDT also looked into ultrasonic, thermography, eddy current, and then today we will be looking into radiography, which is nothing but X-rays and gamma rays. And then of course, dye penetrant, and visual inspection. Okay, this is what we are going to now. If I take the look at the electromagnetic spectrum, ultrasonics. Thermography was mostly by IR waves, ultrasonic was by wave beyond 20 kilohertz or in the megahertz range to be precise. Of course, there was one acoustic emission also, which is again in the range of maybe 2 to 5 megahertz. And eddy current, of course, it depends on the magnetic field. But looking at the frequencies of ultrasonic, IR waves and the acoustic emission, these waves X-rays and gamma rays are very high frequency waves. They are of course, they are all electromagnetic waves. However, their wavelengths are very small compared to the wavelengths of IR waves, ultrasonic and eddy acoustic emission. So, because the wavelengths are small, they are in fact smaller than the interatomic distances. Okay. So, they carry high energy. Let us see what is the characteristics. So, this characteristics of X-rays and gamma rays are they have a much lower wavelength than the visible light. As you know, visible light has an wavelength from 4000 to 7000 angstrom, and infrared somewhere between 9000 to 1400 14,000 angstrom, but compared to that they are on the other end of the spectrum where the wavelengths are very less, and of course, they travel in straight line, they contain high energy, okay. And the best part is they cannot be deflected or changed by the presence of any electrical or magnetic field. However, since they have such high energy in them, they can penetrate materials, and this penetration power of these waves of this X-rays or gamma rays depends on the frequency of that particular wave, and of course, the material density also comes into play, and their intensity of course obeys the inverse square law, like we have in the case of optics, like in the case of acoustics, and they are highly dangerous because they can penetrate any materials. They can also endanger human beings who operate this equipment, and they can enter and destroy the cells of the human body, and then can cause irreparable permanent damage if the exposure of the human cells to these waves, X-rays, are there for a longer time or for a at a shorter distance because of the inverse square law. So, one has to be very careful while using X-rays and gamma rays. I will come to how, what is the difference between X-rays and gamma rays. So, the way X-rays are produced is suppose an atom is there, and then there are electrons on the outer cells, and if energy is applied to these atoms, what happens through an electrical field? These atoms in the K shell, these electrons in the K shell will come down to a lower state, okay, and but since this is a unstable stage or unstable orbit, they will emit, they will bounce back and they will emit certain waves which are essentially X-rays. So, one atom of a material has to be bombarded with electrical energy, and then these X-rays will be produced. Okay. As opposed to gamma rays are something because of radiation of certain materials, these gamma rays, the alpha, beta gamma rays, they are radioactive. Okay. And of course, a small quantity of radioactive material can be used to produce these rays. They are because of a nuclear radiation, they are harmful if not cared for, but they have more energy, more penetration power, and if these waves are carefully controlled through proper optics and electronics and focused onto a particular spot, they can be used for many fusion operations, cutting operations, etc. In fact, you must have heard of the gamma rays used in surgery, okay, but they are radioactive. That is the factor for which we have to be careful while using gamma rays for NDT. Though people use it because a small amount of nuclear material can be used to generate gamma rays, and then they can be controlled and used for NDT testing. Okay, because the key word, be it X-rays or gamma rays, is that we use the energy of these waves to penetrate a material. Now, what happens, like we had in the case of ultrasonics, suppose we have a material where there is a void, okay, that is of a different density, or we have a foreign particle of another density, of a higher density. So, if the X-rays are incident on this material, they are going to penetrate, okay, and because of the density difference, what happens? The intensity of the X-rays at this location will be different then this location. So, if we have some sort of an photographic plate, and then we will maybe if I draw this on the top view here, I will get an image as to this some image, this is another image. So, this is the shadow, if you can say so, of the foreign particle or the void present in the material, and this is very handy. This is similar to the X-rays which the doctors do, for example, for the human hand. I mean, we can find out the bones, okay, by an X-ray. Because this is the flesh and this is the so called bone. So, there will be a density difference. So, the penetration of these X-rays depend on couple of things, and that is the power of the X-ray in terms of the distance from the X-ray source to the material, in terms of the time of exposure of this material to the X-ray waves, and then with this image can be formed on an X-ray film or like photographic film, or nowadays of course, people are using computers, digital imaging to capture these X-ray images, and then of course, there is a method known as tomography, okay, wherein you can have a digital image captured through a computer of the X-rays which are incident on a material. So, to summarize the properties of X-rays and gamma rays which makes them useful for use in NDT is because they have low wavelength, high frequency, they can travel in straight paths, they have high energy, they can penetrate materials, obey the inverse square law, and they are risk to human being if not cared for. So, this property of X-rays help us in using them for NDT techniques. So, what is this radiography? The radiation used in radiography testing is a high energy, shorter wavelength version of the electromagnetic waves that we see as visible light. The radiation can come from an X-ray generator or a radioactive source. So, if I look at this electromagnetic spectrum here, this is our visible range right here. Below that is the infrared and then the microwaves and radio waves. These have a little higher wavelengths, of course, than lower frequency, as opposed to we have the UV rays which have a higher frequency than the visible lights. Then we have the X-rays and the gamma rays. So, the gamma rays shorter wavelength, more powerful, X-rays a little less powerful than the gamma rays, and this is how they are positioned in the electromagnetic spectrum. Now, mind you, the speed of all the waves is the same as the speed of electromagnetic waves, and that is 3 × 10⁸ meters per second. Now, how is this X-rays generated? Okay. So, what we have here is an animation of this. There are two electrodes, one as an anode and a cathode. Okay. So, we generate a very high voltage, we pass on high voltage, which could be few thousand kVs, kilovolts, okay, of energy, and then this is that in terms of electron volts, maybe 10,000, 100,000 electron volts. So, because of this material, X-rays will be generated, and because we give such high energy to this electrode here, it gets heated up. Okay. And usually tungsten is used as one of the anodes which generate the X-ray. So, there is a tungsten metal element here, but because of this high energy, this gets heated up, and for the generation usually this will get oxidized. So, this chamber is actually a vacuum, okay, with a nice glass, and then this electrode has to be cooled. So, there are two important elements in an X-ray generator. One is the high voltage source, other is the tungsten electrode, then we have the vacuum tube, then we have the cooling system, because we will have the focusing system, and of course, the exposure control and the electronics control and associated electronics. So, an X-ray generator needs to have all these components. And finally, we have a material on which these X-rays are exposed. So, we will get an exposure recording device, could be a film, could be a digital image, okay. And that is what it is. Though in the we have to bring in the component whose X-ray is to be done to a facility where this X-ray generators are there, but there are also portable X-ray generators in the field which can be used to do the in situ X-rays, but I understand they are not very convenient and are not very user friendly in that sense that I can take the X-rays to the field. But the component, particularly in NDT, suppose we have a boiler tube, okay. Suppose there are some scale formations, okay. We can do the I had mentioned to you regarding the ultrasonic to measure the thickness, but they can have an X-ray exposed to this. So, radiography of boiler tubes is one application where X-rays are done. Okay. Now, because eventually everything depends on the energy. So, that depends on two important factors, distance and time. Time, by time I mean the exposure time. But again, suppose we have to be very careful while handling X-rays and more careful while handling gamma rays, because gamma rays are radioactive. So, we have to have good amount of shielding, so that of course, the human beings are not exposed to the industrial X-rays. Okay. These X-rays, we have the medical X-rays and the industrial X-rays. See, medical X-rays are the X-rays which we used in the hospitals, suppose to find out a broken bone of a person, whether the bones are intact, whether there is a fracture. So, that is what we use it in the medical X-rays, where the energy of the X-rays are less, because the density of the bones or human flesh is much less than the density of certain industrial materials like steel, aluminum, copper, etc. So, these are of high energy. Now, you can well imagine if this industrial X-ray is exposed to a human being, the cells may get damaged permanently. So, one has to be very careful even while doing the medical X-rays. Those of you who would have experienced medical X-rays, you would have seen how the operator takes care that he is not unknowingly exposed to X-rays, because another dangerous things about X-rays is they cannot be seen, heard, smelt. Okay. So, this is very dangerous X-rays. So, not that a flash of light will go and then you have an X-ray. It is not that. So, X-rays cannot be seen, heard, smelled. So, this is the important parameter which we have to keep in mind while handling X-rays. Okay, we would not know whether an X-ray has been generated standing in front of the equipment. So, we have to be very careful. Okay. Now, because the industrial X-rays are of high energy, we have to be careful. And usually, one particular thing or guard people use is this lead or any material of a higher density. Okay, which can absorb the X-rays. Okay. You would have seen X-rays, even in the airport security systems. Okay. Of course, there are portable gamma detectors also. Portable handheld gamma detectors. They are radioactive though. Okay. Airport security systems for screening luggages or baggages, we use the X-rays there and they are industrial X-rays again. So, because the idea is if there is a density difference, you can notice it. For example, if in a suitcase there is a heavy metal, okay, or there is a soft liquid. So, the patterns will be different in the X-ray images, okay, and that is how people can identify objects which are hidden and not visible from the outside. Okay. That is something again which is powerful. Unlike the eddy current is for surface defect. Okay. Ultrasonic has less power than X-rays. X-rays, these both can find out internal defects. Okay. More power, and then of course, we have the gamma rays, which are radioactive, and of course, acoustic emission is only when internal, but only when material is stressed or loaded, is stressed or loaded. So, this is to give you a relative comparison of all the NDT techniques. Of course, thermography is nothing but a surface temperature monitoring. So, now you can understand the relative applications of different things, different NDT techniques which are used to know the status of a machine components. It may not be an entire machinery, but individual critical components, their physical condition, their current condition can be known by using such techniques, and we just talked about X-rays. So, what happens in this X-ray is the part is in between the radiation source and a piece of film. Okay. The part will stop some of the radiation, thicker and more dense area will stop more of radiation. That is what is in the film radiation. So, if I have a defect here and the film, that is what it will look like. So, this has been exposed less and more and so on, and then we can have certain materials as guide plates. So, that there are in fact ASTM standards as to what are the calibration standards as well. Okay, which are available for this X-rays Okay. By the way, many of these materials are from are available in my website iitnoise.com, where we have in our laboratory many of the NDT technique instruments like an thermal imaging camera, an ultrasonic probe, acoustic emission system, etc. Of course, to use gamma rays and it requires certification by the nuclear authorities. Gamma rays, because of the radioactive material we need from the Department of Atomic Energy in our country. Whether we can store radioactive, what care has been taken, because the radioactive material, after they have their useful life is over, they have to be properly disposed of. So, there are issues of that, and I would not go into that, because nuclear safety, radiation safety is another issue one has to be careful about while using these materials, but nevertheless we have to follow the strict federal and regulatory requirements which are there for safe handling of such materials, disposing such materials, using them, operation and so on. So, but then let us focus into X-rays which are mostly used in industrial systems to find out defects. So, the film darkness density will vary with the amount of radiation reaching the film through the test object. So, this is less exposure, that is more exposure, the top view of the developed film. This is very similar to the X-rays many of you would have done at the hospitals, where you had an X-ray done to see the got a film, and this film is nothing but, again it is a process like an ordinary photographic film, but mind you, this is again done in a dark room, wherein all the developing is done, and then the film is washed, the chemicals are washed off, the photograph is dried, and then of course, the doctor puts it against light and sees where are the denser particle, whether the dense particle being the bone in this case, there is a crack, etc. So, these kind of things can be done. And similarly, in the film radiography which is used in the industry, we can have a similar setup, wherein the component under test is brought down to this location here, and then we have an X-ray film. But nowadays, because of the digital image processing, instead of film we have digital images, and there are devices or the table wherein either you can have the, suppose this is a device, either you can have the, this is the X-ray source. You can either have the X-ray source move around in a circular arc around the body, or you can turn the body, and then you can appropriately have an digital image capturing device. So, a 3D X-ray image can be obtained, and this is what is known as the tomography. Okay. And many of you would have done dental X-rays. If this is the jaw, okay, and then you have your teeth, you would have seen one of the jaws. You can see the X-rays move by a computer control, and then you can get the entire image of all your teeth in one go, rather than exposing it individually. So, this kind of modern techniques, wherein this workpiece or material is put on a platform, and a rotating platform is used, or a rotating X-ray source. So, depending on the convenience, this kind of operations are possible. So, at the end of the day, we will get a 3D X-ray for the image for the material under test. So, these are some of the radiographic images of certain components. You can see these are all different machine components, and you can see if internal there are certain metal systems, because there you can notice the density difference. You can see from the back side, these are the black IC chips full of material, denser material. So, this denser material appear here as white objects. Similarly, here the denser material object as white objects here again. So, these are the how the radiographic images or X-ray images of machine components help us understand whether or what is there inside a material. So, applications of radiography, of course, the industrial applications is to find out the weld defect detection, casting defect detection, boiler tube inspection. In the industrial security systems, we use industrial X-rays for screening baggages to find out the density, etc. Of course, these X-ray systems sometimes they are harmful to human beings. So, we have to be careful about how much exposure time we give to that particular component, and then what is the distance of the X-ray source to the component which is being tested. So, some of the safety precautions which we have to take during radiography, I mean on top of it, if there is gamma ray radiography or gamma ray testing, we have to be more careful about the nuclear radioactivity associated with such gamma rays. However, in the radiography, because as I was telling you, X-rays cannot be seen, heard, smelled, okay. We have to be careful that the exposure to personnel is avoided. Lead sheets which are thick, high density absorb X-rays. So, you would have seen there are suits, lead suits which are worn by operators, so that they are not exposed. Sealing of appropriate material thickness, and I have written the word here appropriate, because that depends on the exposure time, that depends on the density of the material, because and then we can decide on the thickness, because there is also a component known as penetration depth. Okay. This follows an exponential curve, because intensity, and this depends, these are all on material property. At any distance x, the intensity of X-ray is given by this, and this is the penetration depth. Okay, for different materials, we can find out whether a half-inch material is good enough or a 1-inch material is good enough to stop the penetration of the X-rays. So, these are available in handbooks for different materials, penetration depth for different materials. And usually out of experience, the operators know that if I have a component surrounded by a material of a particular thickness, and then the X-rays are appropriately absorbed, and then nothing is going to go wrong. So, there has to be always an option to control the power of the X-ray and the exposure time. By power, you can control the voltage to the electrode for generating X-ray and how much of exposure time is given. Those of you who would have gone to for a medical X-ray, there is a button and the guy presses, and there is a light which will glow, and then once the X-ray exposure is over, the light will go off. So, that gives you, maybe it is maybe 2 seconds or 5 seconds, depending on or 1 second, depending on the power and exposure time. And the technicians, the X-ray operators, they know for a human X-ray how much is the time to be given, and of course, same is true for an industrial X-ray. We also have to control the exposure time and the power. Of course, with the careful one note which one has to be careful about is whether the exposure is so high that a lot of heat is being generated. So, there are X-ray systems where it requires intense cooling of the cathode ray tube. Okay. Now, I will come to another technique which is used as an NDT technique, that is the liquid penetrant inspection. So, this is altogether different than radiography, but these are also used particularly when we have a lot of casting. For example, engine cylinder block. The engine cylinder blocks are usually cast. It looks something like this. Okay. These are the 3 cylinder engine, then these are actually holes, okay, and then this is where your cylinder piston are there. This is the piston, and then the connecting rod, and then this is the crankshaft, etc. And these blocks are actually cast, and then there are water jackets casted here. And if there is a crack on this casting on the top, and because there will be gas pressures at high pressures and forces, things with time will leak out. Okay. So, we have to avoid such surface cracks or cracks which are very, very fine, which cannot be perhaps seen by our naked eyes. So, that is where liquid penetrant inspection is done, usually to find out such cracks. So, a liquid with high surface weighting characteristics is applied to the surface of the part and allowed to seep into surface, breaking defects. Okay. So, if a liquid is there, it will seep in and then it will come up to the surface, and then we can know the defects. And then the process is this excess liquid is removed from the surface of the part by a developer, and then actually a developer is applied to pull the trapped penetrant out the defect and spread it onto the surface where it can be seen. So, basically if I was to think of a material where there is a crack, very thin line crack like this. So, I will put a liquid, the green one is the liquid here, and then this liquid is going to come out to the surface. So, I can put a developer, this is my liquid. So, this comes onto the surface, which can be picked up by a developer. A good example would be, if there was a crack, okay, and then you poured some blue ink onto it, and if I roll a piece of blackboard chalk, okay, so the chalk would get the mark of that liquid there. So, this is kind of the principle of this liquid penetrant inspection. Only thing is that sometimes I can have this developer as a chemical, sometimes this developer can be seen through some other things, like a visual inspection is the final step in the process. The penetrant is often loaded with a fluorescent dye, and the inspection is done under UV light to increase the test sensitivity. So, this is the penetrant has a dye which glows under UV light. So, we pour or rub the surface with such penetrants, and then clean it, and wherever there is a crack, this penetrant is going to seep in, and then it will come out to the surface, and we can see it as a glow under UV light. So, very easily you can see a cracked surface can be seen. Okay. This is where we are putting a powder based developer. This is a fluorescent type developer, which is being used to find out the defects in the system. Okay. So, dye penetrant is a very easy and quick method to locate surface cracks. Locate and detect surface cracks which are otherwise not visible to naked eye. So, this developer can be a powder, and the dye penetrant can be made to glow under UV light. Okay. So, this is how dye penetrant, and these are usually done to find out surface cracks in casting. All kind of surface cracks can be detected by such UV lights. So, because so why do we use liquid penetrant? Because it improves the detection of minor surface cracks by increasing their visibility and size, okay, and it provides a contrast against the background. Usually, this background of a material is very dull. I mean, imagine we have a very dark black component, machine component. Very dull black machine component, and if there is a surface crack on it, it may not be visible, okay, to naked eye. So, if we do this dye penetrant, apply dye penetrant on this surface cracks, and then either have a developer which is a powder, or whether we have a glowing dye penetrant, this on this dull black surface, this will glow, and so it provides a contrast against a background, and then we can detect the surface crack. So, some of the basic steps which have to be followed while applying the liquid penetrant is, we have to prepare the surface as if there are no rough surfaces to feel. We have to nicely clean it, degrease it, okay, and then penetrant is applied. Penetrant is let to dwell for some time, so that it actually seeps into the crack or voids which are there on the surface, and then the excess penetrant is removed by just cleaning and wiping it off on a piece of cloth, and then a developer is applied. Okay. And once we apply the developer, this dye which has oozed out of the crack will form an impression on the developer, and then this developer can then be inspected, and then of course, the surface can be cleaned. So, in the you can have, of course, nowadays there are high resolution cameras, okay, but then the cameras, the problem is, unless there is a contrast with the background, we may not be possible for us to detect the surface defects. And so many places, particularly in production plants, where series of components are being casted and going to, for example, an engine plant. I know of an engine plant where they were doing this, and every engine block which came out of that plant was being sprayed by a dye, okay, and then it was wiped off, and then the entire cylinder block was exposed to UV lights, okay, and by a quick, I mean, somebody with an UV light actually moves around and sees, and wherever he sees a glow, he knows that there is a crack, okay, and that is how quick testing of cracks is done. Because imagine if you have bought an engine and there is a minute crack which goes undetected, you can understand the consequence once you have bought a new car and your cylinder block leaks out the charge or the lubricating oil or the coolant, what a mess it would be. Okay. Nowadays, vehicle manufacturers guarantee that nothing is going to go wrong with your car for 100,000 kilometers. So, to take that into account, one has to be careful that such cracks do not seep in because of obvious many reasons, maybe because of a thermal difference while casting, because of some material inhomogeneity, this crack has happened. So, every cylinder block, because once how is the engine manufactured, once the cylinder block comes into place, they put in all the different components, the piston, cylinder, liners, the valves, etc. But before that, the very basic casting itself has to be checked, and this can be very easily done through a liquid dye penetrant test. That is, you expose, you coat or spray with a dye penetrant and then see it under UV light. Okay, and that is what you can do. Of course, innovations can be done to liquid dye penetrant tests, because nowadays we have high resolution digital cameras. This we can have an totally vision based systems. Of course, that will bring us to the next line of our NDT technique, and in fact, the last technique of NDT which I will be discussing today is just the plain visual inspection, and whether we can take the help of imaging systems, optical systems, to have a better image or better viewing of a machinery component or inspect a material machinery component. So, factors influencing the penetrant dwell time is the surface tension of the penetrant, the contact angle of the penetrant, the dynamic shear viscosity of the penetrant, which can vary with the diameter of the capillary. The viscosity of a penetrant in microcapillary flaws is higher than its viscosity in bulk, which slows the infiltration of the tight flaws. The atmospheric pressure at the flow opening, the capillary pressure at the flow opening, the pressure of the gas trapped in the flaw by the penetrant, the radius of the flaw or the distance between the flaw walls, the density or specific gravity of the penetrant, microstructural properties of the penetrant. So, we have to be careful about these things which will influence the penetrant dwell time. Okay. Some of the materials which are commonly tested by LPI, unlike the eddy current or the ultrasound eddy current, where it has to be a magnetic ferritic material, and ultrasonic it could be any material. Materials commonly tested by liquid penetrant inspection are any kind of metals, plastics, rubber, ceramics, glass. There is no end to it, provided your liquid penetrant can actually seep in to the cracks, and it can we can let it to dwell and then ooze out, so that if there is a glow, if there is a dye in that penetrant, it can glow under UV light, or I can apply a developer, so that this liquid is going to leave an impression on the developer. Some of the common flaws detected by LPI or liquid penetrant inspection are the fatigue cracks, the quenching cracks during heat treatment, grinding cracks, overload and impact failures, porosity, laps, seams, pinholes in welds. These are some things very too small to even detect carefully with ultrasonics or eddy current, because the resolutions here are so fine that it may be in the noise floor of an ultrasonic or an eddy current system. So, this kind of tests, a very minute thin hairline kind of cracks on the surface, can be very easily detected by LPI. Okay. So, advantages of LPI is the method has high sensitivity to small surface discontinuities, which was not there in the case of the eddy current or the ultrasonics. The method has few material limitations, example metallic, non-metallic, magnetic and non-magnetic, conductive and non-conductive may be inspected. Large areas and large volumes of parts materials can be inspected rapidly and at low cost. Parts with complex geometry shapes are routinely inspected. Indications are produced directly on the surface of the part and constitute a visual representation of the flaw. Aerosol spray cans make penetrant materials very portable. Penetrant materials and associated equipment are relatively inexpensive. Okay. So, some of the disadvantages of LPI: only surface breaking defects can be detected, only materials with a relatively non-porous surface can be inspected, pre-cleaning is critical since components can mask defects, metal smearing from machining, grinding and grit or vapor blasting must be removed prior to LPI. The inspector must have direct access to the surface being inspected. Surface finish and roughness can affect inspection sensitivity. Multiple process operations must be performed and controlled. Post cleaning of acceptable parts or materials is required. Chemical handling and proper disposal is required. Okay, and this is one of the image of a fluorescent penetrant on a connecting rod. Now, I will come to the last technique of visual inspection. What essentially it does is we can have boroscopes, fiber scopes, magnifying glasses and mirrors to see components which are not visible to us from the outside. So, we can have cameras built in, like we want to do a pipeline inspection, we want to do a cylinder internal dimension checking, like similar to doctors putting in a camera in a tube and doing a surgery. So, this kind of visual inspection aided by cameras, magnifying glasses and mirrors, and of course, now we have also portable cameras, video cameras which can be put in robots and then inspected places where humanly it is not possible for somebody to go in. For example, inside a pipeline which is conveying crude oil or some sort of a liquid, we would like to inspect the internals. So, we can move in a camera, robotic controlled cameras. So, these are what people also use for NDT visual inspection techniques. So, with this I would like to bring to an end the module on NDT, and we basically looked in the 4 lectures on NDT techniques on acoustic emission, ultrasonics, thermography, eddy current, acoustic emission, and of course, now radiography as well. Thank you.